So we're going now on to our next speaker. Our second speaker is Debora Marchak. Debora obtained her PhD in physical chemistry from Tel Aviv University and later joined the departments of materials and interfaces at the Weizmann Institute. Nowadays, Debora heads the We Have Chemistry National Projects Competition and conducts research on Pay Attention, art-integrated chemistry, teaching practices developed by neuropedagogical approaches at the chemistry group of the Science Teaching Department at the Weizmann Institute of Science. Her journey moves from the world of nanomaterial and chemistry through art and education, as Debora teaches and is involved in several projects for the advancement of practical science education in Israel. Let's welcome Dr. Marchak.
Hello, everyone. My name is Debora Marchak. Thank you for the introduction. I'm going to be talking today about how we can fuse chemistry and art in a multi-dimensional grid, a learning grid. I'm going to ask you to please ask questions through the chat so that we can have a question sessions later on. Let's begin with an exercise. If we would meet face to face, then we could do this exercise in pairs, but we don't have that privilege right now. So I'm going to ask you to take a look at the image and pay attention to the elements that you see, elemental parts of the image, and think if there are connections between the parts. Probably you can see there is a pattern. Is there movement represented in the image or not? And finally think if there is an implied meaning or what can be the function of this image. So this for us chemists is a model, is a representation of chemical content at the symbolic level. This image is loaded with specific information which we can decode, for example, to understand systems or answer questions about chemistry. And I hope I gave you a hint of why chemistry can be hard to learn for many students. And that is one reason is that it requires a sort of a thinking switch, a switch in the way we think about things. For us to understand chemistry deeply, we should understand chemistry at different levels. For example, one level is the macroscopic level, which is the level of the observable level, the world we experience, that we can measure. We also have to understand phenomena at the sub-micro level, which is the level of the particles themselves and what are the interactions between these particles. And we also have to think what's going on in this level according to chemistry. The symbolic level is any representation of chemical content at the symbolic level through symbols. In it can be formulas or equations, drawings, diagrams, graphs, any sort of representation at the microscopic level, symbolic level. And we, of course, have another probably higher level of the process level that is about the dynamics of the systems, of things that are happening before and after. And this implies all other levels. In addition to all this, we have to be able to transition between macro, micro, symbol, and process words. And you can ask yourself, well, where is the problem here? Well, there is a problem because we have to move from a natural language and symbols, thinking through natural language and symbols, which are general, concrete, and macro level, to thinking with chemical language and symbols that are specific, highly abstract, and multi-level, as I showed you before. So it is in a way trying to go against our nature, the natural way in which we think. To exemplify this, ask yourself the question, where does a student go in his mind to answer a question about chemistry? So if you ask a student to describe her room, she will start talking and describing right away. Well, there is a door, in front you have a window, on the right side there is a bed, and on the left side all the clothes are spread on, and so on. But people are not, don't have to remember this narrative by heart, word by word, like an array of words. They just go to a mental representation of a physical space where concrete concepts populate this space, and where phenomena is macroscopic. But if we ask about a chemistry question, then we would like the student to have a representation of content, also sort of an image where they can go and retrieve information with which to answer the question. So for this to happen, we as teachers have to help students construct this picture in the first place, this correct mental model of scientific information. This is where education and neuroscience enters the room, and how can we aid learning of abstract concepts by education and neuroscience. Now, education and neuroscience is a relatively new field of research, where what they do is they take what is known about learning at the neurological level and implement it on processes of learning and teaching. What are the implementations, the implications of neuroscience on learning and teaching? And well, to get into it, we're going to go through this very simplified information processing model, which then we will relate to learning. Whenever input arrives to us, to our senses, this input has to go through a series of filters until it can be successfully stored as long-term memory, and then it overgoes further processing in consolidation and probably learning. And these filters have a typical lifetimes. Like, for example, sensory register is only of a couple of seconds, while working memory, which can be seen as the manager of your desktop, is actually controlling everything. It can be it can last up to 40 minutes or so, and it can efficiently handle up to 10 items. So let's give an example how this works. For example, you woke up this morning with a pain in your neck, and well, if it's nothing, it doesn't go on, you will just forget about it. So out of the system. But if it's something that it keeps, the pain keeps on, you cannot forget about this. So it will go through the filters, and you will have to act upon it. And for example, call the doctor, and then you will try to think, how come that your neck is stiff? Is it the pillow? Is it too many hours in front of a computer? And so on. You will want to learn from this, connect it to other data. So okay, we can say that learning actually is or implies a long-lasting neurological change. Anything that is long-term memory and anything that was learned actually is input that had what it takes to go through all these filters and get into the cognitive belief system you have. It underwent consolidation, and you learn from it. So we can ask then, which are the conditions that support storage, especially when input is abstract? So looking at the literature, we see that there are many principles. I just show mainly 3 of them here. One is repetition. We know that repetition is efficient for learning. So any kind of learning actually is based in some way on repetition, practicing and rehearsal. The principle of use it or lose it is why you forget words of a language you don't use anymore. Then another thing that we know is that for sure any long-term memory has 2 components, a sense component and a meaning component. So the sense component is the feeling of, is the cognitive side of what you make of what arrives to you. It's like the idea of it makes sense, it's clear, I understand that. But the meaning component is more complex, and it has to do with affective and psychological aspects of the process of assigning meaning, personal meaning, not verbal or non-verbal meaning, to an event or to any input. So here, this creates a sort of a very well-known experience for teachers, where, for example, they had a great lesson, students were engaged, they seem to have understood the content, and they do worksheets just fine, they do great in the exam. And after a while, when time goes on, they just forget about the content, and especially after the summer, it's like it was erased. And this is because teachers, we tend to plan our lessons so that they are clear, and this is amazing. But what about the meaning? Are we allowing students to connect it to previous meanings, probably, or to construct meaning out of it? And we cannot, what is the problem here is that we cannot say what meaningful is. It is very personal for each of us. So it's not even enough for me as a teacher and saying, this is very important, this could save the world. But probably that's not just in the best of the interest of students right now. They don't see why that's okay. In terms of processing, at the processing level, multiple modes of learning will be more efficient than single modes of learning, or especially choosing some channels as modes of learning. For example, lectures or taking notes are two modes of learning, but if we add here sensory motor functions, for example, we could be opening more channels to broader processing of information through different channels, of course, and make more connections. So what you can see here is basically that from every one of these principles, you can start thinking about what can be done. How can this be, will this influence the way I teach in my class so that it influences the way students learn, especially abstract content. And this is true. It could be a good way to go for any subject area, not just chemistry, of course, but we are interested right now very much in chemistry. So the chemical content that was encoded in an image and that the students has to decode requires probably a sufficient setup, a more holistic setup that allows students to build correct representations of content at the abstract level and as mental models, of course, and then decode this information, these images. And we, as I said before, auditory and visual alone are not enough for most students, are not enough for mastering the whole spectrum of skills that are to be mastered to understand really deeply chemistry. So also, if we go to the literature, especially in arts integration, we can see that there are some methodologies. What we can do is add visual thinking strategies and tackle them explicitly. Teach visual thinking strategies. Another way we can do that, we can help this process of understanding, is unusualness of input. Make input more unusual and exciting, probably, and surprising. So rise level of attention, something is going on, I'm going to pay attention to that. And also rise motivation to come to chemistry because they don't know what's going to happen next. Varied processes, varied processing, so that means not only, let's say, intellectual, but also sensory motor channels. And creative elaboration, meaning that, okay, put content to use, but not just through worksheets. Put content to use in a creative way. Elaborate content in a creative way. And all this to, of course, we want to rise sense and meaning components of input. What I didn't include here in this slide is actually the social and active learning. I will probably say something about that later. Okay, so this is where the idea of a multi-dimensional, multidisciplinary learning grid for learning chemistry crystallizes. As you can see here, we have a sort of a space, a conceptual space, created by the intersection of three disciplines: the chemistry, neuroscience, and arts. And this space would allow us as teachers to develop content that is more holistic and that involves or induces a learning experience that can really support the mental processes needing to understand chemistry, as I explained them before. And you can ask, but why not just use chemistry and neuroscience? And that would bring us to a two-dimensional grid. And that could probably work as well. But in my opinion, the way I see the world and the way it crystallizes in my mind is that the arts actually, and elements of the arts and elements of the methodologies that you have in arts to analyze what you see and the aesthetics experience that you can bring is actually a perfect third dimension to design or to take into account to give the tools to students, actually imparts tools. And not just that, also rise them, help the meaning-making process, and or at least connect this activity with previous meaning that a student can have about something. So, arts integration here rises or emerges as a tool to understand chemistry or to help students understand chemistry. And let's have now a taste of what, how does this look actually in class. So if one of my students, as you can see here in the picture, we would start actually with a carefully curated artwork, and we would do some variation of a deep observational exercise, and we would analyze the image. Only then, here we are gaining visual literacy not connected to chemistry, and only then we would move to images with content, chemical content, and do the same thing, the same kind of exercise of appreciation of the image. So in these exercises, and regardless the nature of the image, we are asking students to stop, give time to that interaction between them and the image, try to go through the basic elements of the image, the interactions there may be between these basic elements. Are there emergent patterns which they have a meaning in chemistry? Whole meaning of composition, things like that. We build up the way in which they analyze a picture. And I know that this actually exists and is done a lot to generate knowledge, understanding, and meaning in the arts. It's part of art appreciation techniques. And I think that it would be perfect also to gain general knowledge, gain understanding, and assign meaning in chemistry as well. So I saw that there were potential shared cognitive skills that students can also only benefit from them. So specifically, as I show you here in the grid, you can see that I pinpointed some of the elements from each discipline that could help to design this activity. And what you see here is actually the first exercise and the second one, I talked about them, but the third exercise is now implementing, or more accurately, using these new gained skills in an exercise that would ask from students to actually ground what they learn to exercises at the level of the matriculation exam in chemistry. Because otherwise, this approach is, it could be a gimmick. It would be something very nice, a great experience, but we have to ground it and connect it explicitly to chemistry. And probably I will have time to talk about that in the end. Okay, this is another visual thinking strategy activity where the main thing we want to tackle is inquiry skills. More specifically, laboratory inquiry skills, but out of the context of the laboratory. We can always learn those skills not related just to doing the experiment itself. So, inspired by this beautiful image of Salvador Dalí, we encourage students to go from asking general questions to asking chemistry-related questions and formulate a research question and then design an experiment that would test this question. And in addition, you can see that, okay, when I chose this picture, I saw the connection between this picture and the subject of chemical materials. And so I also developed the activity to revise that content, which was learned a year ago. But it was okay because, as we said before, we also have to practice, rehearse things that we learned in the past. Other teachers that took part of the professional development course that happened during this summer They actually thought that this picture would be great for environmental chemistry or thermodynamics. So as you can see, when a teacher curates the images he wants to bring to class through this approach, he also has to understand by himself what could be the connections between the images and chemical content. So what you see here is actually sort of, these are creations that my students made in an activity where they are asked to craft using some material which they choose. It can be wood, it can be sugar, it can be soap, it can be whatever you choose. And then analyze the process of creating these crafts in relation to the chemical properties of the material at the macroscopic level and also at the microscopic level. So these creations are accompanied by an essay. Students write an essay at the level of the matriculation exam, at the level required by the matriculation exam, where they specifically analyze the microscopic structure of each material and how it influenced the macroscopic structures and macroscopic properties, and how these properties affected the way in which they crafted. And well, generally we do a museum setup in school. We get the lab and we turn it into a museum for a day, and students from all over the school can come in the active breaks. But this year we can't do that. So we are having a photograph exposition, as you can see here, these beautiful photographs of materials, of crafts that my students prepared, and this is very fresh. They are going to present this actually this week on Thursday. Well, we also have crafting at the microscopic level. I mean, crafting representations of content that comes from the micro level of understanding chemistry. And actually here, well, this is a traditional practice. You can say, well, what's the difference? Many teachers do this kind of activity with their students. But here we developed we modified the traditional practice to include explicitly neuropedagogical aspects and also design language. For example, we go through the process of designing this kind of models. Sometimes we work with plastic models, and what a designer of these kinds of models, because actually designers work on that, would have to do. They would have to sit with a chemist and find a shared language, right? Also some math. Well, this I cannot go very much into detail now. And what you see here is a last example. Here we have actually, well, I think I have time to play these sounds. I'm going to explain what this is. This is actually a task where we ask an activity where we ask students to create sound representations of chemical content. So the students have to think what can be that, what can be attached, what kind of sound I would attach to, for example, a solid, a liquid, or a gas. And can I play? Okay, so let's see what Reut did for the solid.
I'm sorry, Deborah, but it seems like we cannot hear it in here. Maybe the audio is not shared, but we cannot hear it.
She chose to differentiate between solid, liquid, and gas by the movement a particle would have or not have in any of these three states of matter. And Robert, for example, decided to actually differentiate the solid, liquid, and gas by the macroscopic properties. So he just depicted the sound that a solid would have, a liquid would have, or a gas would have. And Michael, for example, he chose to differentiate the matter states actually by the energy, internal energy, each matter state would have relative to one another. So as you can see here, students have many ways of representing this same subject, this same solid, same liquid, same gas. This is after we learned collision theory and thermodynamics. And in the end, they said, they spontaneously reported that they never thought about representing chemical content through sound. They never thought about that before. What kind of sound would have a particle in a specific state or a system? Or what kind of sound would have a process, okay? So I just barely mentioned before that in addition to arts integration, we, when these activities were developed, the social and active learning aspects were very much involved. And that is because of the affective aspects of learning that they can induce. But not only that, also because they invite students to talk and argument and negotiate content when they work in groups. And a word of caution here has to be mentioned. One of the things that you see here is in these pictures is that students are really engaged. But the fact that they are busy or engaged doesn't necessarily mean that they are learning something. They are into it, okay. But we have to ground later on explicitly these activities to chemistry. And we do that with follow-up exercises and worksheets that were designed so that students can apply the skills, the knowledge that they gain during the arts integrated activities actually to solve a problem that would appear in the exam at the correct and at the highest level possible. Because otherwise, it would just be a gimmick. So this grounding of the approach to actually the exam is in the end what makes it not be a gimmick. What makes this useful, a rigorous approach, an approach for learning till the end. Well, another thing I want to mention, I don't want to forget that, is that we don't teach that, like that all the time. There is a very respected place, in my opinion, to traditional learning, and it has to be kept. But what we can do, and we do, is we bring to the chemistry class different approaches to learning in a modular manner. So we have traditional lecturing, for example, we have traditional worksheets, yeah, and things like that. We also have inquiry labs, which are great in itself, and they can encourage and impart a number of skills in themselves. And then we also have, what I propose here is to arts integration, right? I propose to integrate arts and this approach as a part of another player in the way in which we expose content to students and let them learn. Okay, so, all right. Look, learning chemistry, I talked a lot right now. I feel I talked a lot, so I'm going to summarize. Learning chemistry asks for constructions of content that is, most of it is abstract. So students have to build correct mental models to which to refer later on when they have to answer questions in chemistry. Art integration emerges as a tool, in my opinion, perfect tool, to aid this process and also build meaning. Chem-art fusion is in line with processes that support learning by education and neuroscience. And this multidisciplinary grid, this conceptual space, can help also content developers and teachers design holistic chemistry learning experiences, design those experiences that would foster understanding in chemistry at the required level. All right, so thank you for listening. I apologize if there were any technical problems, and I invite you to ask questions. You can also contact me through email for ideas and questions and anything you want to discuss. Thank you.
Thank you, Deborah. I don't know about our guests, but I wish I'd had a teacher like you at high school. It was fascinating. Okay, we have time only for one question. So if you don't mind, I'd like to ask it on behalf of our guests.
Sure.
Deborah, you've moved between several fields in your journey of education. What, in your opinion, are the priorities in science education? If you had to write a program now, what would you do first?
Oh, that's a great, okay. So the answer would vary if you asked about science programs for different ages. Because what I think happens right now, and I'm going to talk about high school because that's where where I do. And I think that today students get to the university and probably have to relearn many things. But in high school, we sometimes feel as teachers that we don't have enough time to teach things at a deeper level. And I think, personally, that this is not completely true. The curriculum, I think, is very beautiful. If you go through the subjects we learn, they give a broad understanding of what chemistry is. And they do prepare children. They at least expected to prepare students to go to the university, but not just that, also gain skills in general thinking and scientific thinking. But the problem here is that, in my opinion, it doesn't have really sort of levels. What this approach could do is we could, instead of bringing another worksheet, we could bring the same amount of time, right? We could bring something that would ask for the student to an extra push. And especially, I'm not talking about the stronger students because they have another mechanism of thinking. I'm talking about those students that like chemistry very much, and we are going to miss them after that. Probably they have these misconceptions about, no, I cannot really go to the university or the industry because it's okay in high school. And in order to do that, we should teach them also really how to think. Sometimes, where you can see this sometimes is when they do an experiment, and they love experiments. And when it comes to the part of explaining the phenomena that they see, they just did the experiment. So explain the phenomena at the microscopic level, and then write the matching equations or formulations at the symbolic level, they are stuck. So this gives you an opportunity, this approach, to actually sort of make the connection between these two words. I wouldn't write a new program. I think the program is great. I would work on giving teachers tools to think about more levels while implementing. And I also want to add some very, very, this exercise I showed you, and which we do in pairs, can be like 10 minutes. A 10 minutes exercise, an exercise or 5 minutes, they think about something. And this spark lasts on. That I think I answered the question. I wouldn't change the program. I would change probably give more tools to teachers.
Well, that's you've given me a lot of thought, and I'm sure the other guests a lot of food for thought. Thank you very, very much. It's been wonderful.
Okay, thank you. Thank you.
Okay, have a good day. Thank you.